Hi everyone. So for today, I will be showing you in order how to solve for first order homogeneous differential equations by substitutions. And now let's go on to the first example. Hi everyone. So this is our first example for today's first order homogeneous differential equation. We've got here dy over dx equals to x plus y over x, and our very first step to solve this differential equation using a substitution is changing all of the variables here, which are x's and y, into a single variable that I would like to call it as a u here, which u is equals to y over x, and you will see why I made the substitution of u is equals to y over x. And our dy over dx here, we will substitute it with our dy over dx here because this is a result of the product rule of y equals u times x. And after we've determined all of our substitution variables here, we're good to go and we can solve for this differential equation using a substitution. So first, let me rewrite this differential equation so you all can see clearly what's happening here. Yxn is equals to x over x plus y over x. Yxn is equals to x over x is 1. Y over x here, we know that our u is equals to y over x, so we can substitute it for u. And so what's left is we need to substitute our yxn with dy over dx here, which is u plus x times uxn or du over dx equals to 1 plus u. And then I would like to subtract both sides with u, and we will get x times uxn equals to 1. And from this step, you'll see what are we going to use as a method to solve for this differential equation. Clearly, if I write it down like this, you will notice it right away what method we can use. So x times d over dx equals to 1. And from here, you all know that we will use the separable method again, which we're going to separate the u's with the u, du, and we're going to spare the x's with the dx, and we're going to integrate the x with respect to dx, and we're going to integrate the u's with the du. Okay, so let's multiply both sides by dx over x, and also this side too by dx over x, and then we will cross out the x's here and also the dx here. We will get 1 du, or just du, but 1 times du is equals to du equals to 1 over x dx on the other hand. And so from here we can just integrate them using the separable method. The integration of 1 du equals to the integration of 1 over x dx, and 1 du, the integration of 1 du will equals to u. The integration of 1 over x is just ln x, and don't forget to add the constant here, or just add the constant to one side, not to both sides, because remember, again, constant plus constant is just a constant. Okay, but wait a minute here, we want to make this equation into a y equals equation, and how would we do that? We see our x here, so we know that our right side is fine, but we've got a u here, and what will we need to substitute u for? We know at the start of problem we've set u equals to y over x, and so we can make another substitution here, u as y over x equals to ln x plus c, and so we can multiply both sides by x to get rid of the x on the left, and we will get here a y equals equation as our final answer. Y equals x times ln x plus c. And so this is our final answer, or our general solution to this differential equation. Hi everyone, so this is our second example for today's first order differential equation by substitutions. We've got here y squared plus y times x times dx minus x squared times dy equals to 0, and we're still gonna use the same exact substitution variables like the previous example, which is u. So first, you all may see or you all may think that this is in a form of an exact differential equation, but we know that if we take the partial derivative of f with respect to y here, it will give us 2y plus x. And if we take the partial of f with respect to x here, we will get negative 2x. And clearly, this is not an exact differential equation because my is not equal to nx. Okay, so we need to use substitution in this way. I would like to first multiply everything here by 1 over dx, so that will give us dy over dx. And let me rewrite our differential equation here. Y squared plus yx, okay, times dx. The dx will be crossed out here, minus x squared times dy over dx equals to 0. And this is what we wanted, because we want to substitute later with this thing here. Okay, so after transforming our original differential equation into this one here, now we want to transform or change all of the variables that are the y's and the x's into a single variable, which is the u variable. Okay, so first let's try by dividing everything by x's, and just from this step we can see that our first variable here, y squared over x, will still gives us a y, and we don't want that because we want to transfer everything into a u and x's that we can use a separable method later on. And so let's try changing our substitution variable, which we have u equals, but now let's change it to u squared equals y squared over x squared. Okay, so now let's multiply everything here. Let's multiply everything here with 1 over x squared. And we know that y squared over x squared here is just u squared plus y times x divided by x squared. We can cross out the x and it just leaves us the denominator with x to the power of 1. And so y over x is just u minus x squared divided by x squared is just 1 times dy over dx equals to 0. And now we're safe because everything is already in the form of u variable or in a single variable. But let's move or let's subtract both sides by y-axis or dy over dx. That's the same thing here because we want to make our y-axis positive, not negative. Y-axis equals to u squared plus u. And now we just need to substitute our y-axis with our dy over dx here. Okay, so we have u plus x times du over dx, which is u-axis, equals to u squared plus u. And we're gonna subtract both sides by u to remove the u on the left side here. And so x times u-axis equals to u squared. And from here on, we know that we can simply use the separable technique that we've been using. And so x times du over dx. I like to rewrite it like this one so you can see more clearly the algebraic process of doing it, equals to u squared. And so let's multiply both sides by dx over x times u squared, and also this side as dx over x times u squared. And so after multiplying both sides, we know that we can cross this one, we can cross this one, and so we can cross this one as well. And it just leaves us with 1 over u squared times du equals to 1 over x dx. And so we just need to integrate both sides. The integration of 1 over u squared du equals to the integration of 1 over x dx. 1 over u squared du will gives us negative 1 over u as integration equals to 1 over x, which just gives us ln of x plus c. Don't forget the constant here. And after this step, it's just clearly easy, like what we did in the previous example, which is substituting the u with the y over x here, like what we've stated in the early part. So negative 1 over y over x here equals to ln x plus c. And we know that 1 over or negative 1 over y over x here will gives us negative x over y equals to ln x plus c, and multiplying everything clearly by y over ln x plus c, and on the other hand too, multiplying by y over ln x plus c will gives us our final solution, or our general solution for this differential equation, which on the left hand side our y will cross out, and our right hand side our ln x plus c will cross out as well. And so our final solution is y equals to negative x over ln of x plus c. And this is our final answer for example number 2. Hi everyone, this is our third example for today's first order homogeneous differential equation by substitution. So we've got here x squared plus 2y squared times dx over dy equals to x times y. And we've got an initial value problem of y negative 1 equals to 3. And since this has a initial value condition at the start of our problem, we know that our final solution or final answer will be a particular solution. And so we're going to use the same substitution, which is u as a single variable. And let's start by multiplying all of the equation here by dy over dx, since we want dy over dx to be substituted, not dx over dy. And so by multiplying everything by dy over dx, we will get on the left hand side x squared plus 2y squared equals to x times y times dy over dx is just y accent. Okay? And afterwards, we want to change or transform all of the variables that are x's and y's, like in the previous examples, into a single variable that we've got here, or we've determined here as a u. Okay? But if we divided everything by x here, we still got a problem. We will still be left by a single y variable, and that we don't want. That's why let's multiply everything by 1 over x squared, and that will take care of the y squared here, which our substitution will be u squared equals to y squared equals to x squared. Okay, so multiplying everything by 1 over x squared will gives us x squared times 1 over x squared is just 1 plus 2y squared over x squared is just 2u squared. Okay, equals to x times y divided by x squared is y over x, which is just u times y accent. And so we want to make this equation to y accent equals to, let's multiply everything again by 1 over u. that will give us y-axis equals to 1 over u plus 2u, or let's just combine the fraction as 1 plus 2u squared over u. And let's not simplify this yet first, because we need to substitute our y-axis with our dy for dx here, and you'll see why. So our y-axis is u plus x times d over dx, which is just u-axis, equals to 1 plus 2u squared over u. And so let's subtract both sides by u, the left hand side and also the right hand side by u. We will get x times u xn equals to 1 plus 2u squared over u divided by u over 1. And if we want to make the same denominator, we can get as 1 plus u squared. And so from here on, we can just do the separable method. Okay, let's also make this u-axis or break it up into du over dx, so it will be more clear as a separable method, equals to 1 plus u squared over u. And let's multiply both sides by, on the right hand side and the left hand side, let's multiply it by u over x 1 plus u squared, and also multiply it by dx here. And for the other side, we're going to do the same thing, which is u dx over x times 1 plus u squared. And so on the left hand side, our dx will cross each other, and also our x's will cross out with each other. And our right hand side, our 1 plus u squared will cross out, our u will also cross out, and it will leave us with u over 1 plus u squared times du equals to 1 over x here dx. And so we can just integrate it, which is the integration of u times 1 plus u squared negative 1, because we brought it from the denominator into the numerator, du. And you can see on the left hand side here, we can just use the throwback method. And for the right hand side here, 1 over x dx is just ln x. So for the left hand side, let's do it over here, which is the integration of u 1 plus u squared power of negative 1 du. Let's try taking the 1 plus u squared, taking the derivative of 1 plus u squared here, which just gives us 2u, and we can see that we can cross out our u here. And so after you cross out the u's, our integration for the left hand side will just be 1 over 2 ln of 1 plus u squared. And so this is for the left hand side, and our right hand side here, 1 over x dx will just be ln of x plus c. And so we would like to rewrite our 1 over 2 ln 1 plus u squared here, becoming the ln of 1 plus u squared to the power of 1 over 2 equals to ln of x plus c. And you'll know soon enough why I change the form of 1 over 2 ln here to the ln here. So basically we've got two ln's in the both sides, and if we put c or e exponential in the both sides, we can cross out the ln, and that's why let's put e onto the both sides. The power of ln 1 plus u squared to the power of 1 over 2 equals to e to the ln of x plus c is just e to the ln of x times e to the c. Same thing. And remember, e to the c or e to the constant is just a constant. And here on, we can cross out the e to the ln, and this just leaves us with 1 plus u squared to the power of 1 over 2 equals to c times x. Okay, and from here, let's square both sides to remove the square root on the left side here. Okay. After squaring both sides, this will give us 1 plus u squared equals to cx squared. And subtracting 1 from both sides too, this will give us u squared equals to cx squared minus 1. And we know that our u before, or u squared, is equals to y squared over x squared. And now we can rewrite our u squared here as y over x squared equals to cx squared minus 1. And from here, let's try substituting our y's and x with the initial value condition and simplify it later for a y equals equation to make it easier for our calculation to find the c here first. And we know that our x will be negative 1 here and our y will be 3. And so, substituting in for x is negative 1 and y for 3 here, we will get negative 3 here, negative 3 squared, equals to c times x. X is negative 1 again, but negative 1 squared is just 1. So this will still be c squared minus 1. And so negative 3 squared is 9. And c will equals to, or c squared will equals to 10. And c will just equals to the square root of 10. And after getting a c here, it's pretty simple because you will just need to substitute the c here with the value that we've got just now. And so we will get y over x squared equals to 10 x squared minus 1. And so square rooting everything, since we need the square on the left hand side to be gone, we will get y over x equals to the square root of 100 x squared minus 1. And from here, oh, actually, this is square root of 10x, and this will still just be 10x squared minus 1. And multiplying both sides by x to get rid of the x on the left hand side, this will give us y equals to x times the square root of 10x squared minus 1. But wait, this is not the final answer yet. Remember to check the initial value condition, since this is in a form of square root where it is plus or minus. And since our x value here is negative, our final answer as an explicit answer will be negative x times the square root of 10x squared minus 1. And this is our final answer, that is in particular solution. And this is how you solve for example number 3 to first order homogeneous differential equation by substitution.